All right, moving on to our next talk. It is Andrea Nelson, who will be talking about research from the Laboratory of Space Systems and Optomechanics, or LASSO.
Thank you. Good morning, everyone. My name is Andrea Nelson. I'm a research scientist and program manager in the Laboratory of Space Systems and Optomechanics in the Wyatt College of Optical Sciences. Our PI is Dr. Felipe Guzman. We're located in the basement of this building. Actually, I'm probably standing right above our lab right now. So we work on, it's probably easier to look over here. So we work on novel optical, optomechanical, and quantum technologies for aerospace science and engineering. This includes laser interferometers, accelerometers, relative gravimeters and gradiometers, and other quantum technologies for enhancing inertial sensing. So today I'm going to be talking about 4 of our projects that are kind of related to space-based projects, since this is the Space Institute Symposium. So 2 of the kind of broader missions that some of our research relates to are the LISA mission and the GRACE mission. So on the left is the LISA mission. If you're not familiar with it, this is the Laser Interferometer Space Antenna. This is intended to be a gravitational wave observatory, that is based in space. So it's planned for launch in 2035. A lot of work has already gone into it, and some of the work that we do is contributing to the preparation for that launch. Another project a space-based project that some of our research relates to is the GRACE and GRACE follow-on missions. This is a mass change mission that is essentially mapping the gravitational field of the Earth. There's 2 spacecraft orbiting the Earth and measuring those gravitational pulls. And this is essentially measuring how water is moving around the globe. So I mentioned the LISA mission. One of our previous PhD students, he just finished last summer, worked on an optical truss interferometer. And the purpose of this was to measure the stability of the cavity of that the LISA telescope. So you can see here, the LISA telescope is a constellation that forms a triangle of 3 spacecraft. And between those spacecraft, there is a laser interferometer. So in order to ensure that you have enough stability in the system, you want to make sure your laser telescope is stable enough to read out those displacement measurements that are measuring distances on the order of 2.5 million kilometers. So his project was creating this optical truss interferometer to measure the stability of the cavity of one of those telescope mirrors. And we see here on the plot on the bottom right that he successfully was able to reach those LISA requirements. Now, moving on to other research that we work on, this is predominantly what most of our group works on, are our low-frequency optomechanical accelerometers. So these consist of a test mass on the end of 2 leaf spring flexures, which oscillate in a linear fundamental mode and are read out with a heterodyne interferometer unit. This heterodyne interferometer unit was developed by one of our past PhD students, and it fits directly onto the frame of our resonator. Now these systems can be used as linear low frequency, highly sensitive optomechanical accelerometers. So we see here in this plot, the blue trace is our best to date sensitivity of our one of our clamp system. So this is kind of showing it in relation to other highly sensitive accelerometers in these lower frequency bands between about 1 millihertz up to 1 hertz. So I mentioned that GRACE mission before, the Gravity Recovery and Climate Experiment, with those satellites that are orbiting the globe, at the center of those spacecraft. So those spacecraft are measuring the gravitational field of the Earth, but that's not the only force acting on those systems. So there needs to be something on those spacecrafts that can measure the non-gravitational accelerations that the spacecraft experiences. So at the center of both of those spacecraft is a very sensitive accelerometer. Those are the Onera accelerometers in this plot, labeled as the GRACE and GRACE follow-on accelerometers. So we see also this red trace and this blue trace. So this red trace is actually what our expected best sensitivity that we could achieve with our current measured with our current mechanical quality factor of our resonator. So in a less noisy environment, so if we're not directly underneath us on ground, so somewhere such as in space, we expect our system to be able to reach these levels of sensitivity. So this is a competitive, smaller, lower weight, lower power accelerometer that is still very highly sensitive at these accelerations. So I showed that plot. This shows it a little bit in different units. So we have an RMS noise sensitivity on the order of 8 picog's above about 60 millihertz, excuse me. And so on the left here, we see our one axis 5 hertz resonator, which are also working to expand out into a triaxial system. So seen here is our XY system, which is a biaxial accelerometer. And these systems are at a TRL5 level prototype. So I mentioned that triaxial accelerometer. So we're working to expand these uniaxial systems into a triaxial system that can measure 3 linear accelerations. So all 3 directions of sensitivity. So we have this top layer is our XY, which has 2, I don't know if there's a laser pointer on here. That's okay. You can see the 2 sensors that are oriented in 90 degrees to each other. And on the bottom layer, there's an out of plane Z axis. So all of these resonators have the same fundamental frequency, and we anticipate them to have the same, essentially the same sensitivity as our single axis 5 hertz that I showed before. Now I mentioned our sensitivity. On ground, we are actually currently limited by signal with this system. So one of the things we like to point out here, you see between this 100 millihertz and 1 hertz range, we have these spikes in our signal. Now what this is a very well documented signal. It's called the microseism. It's the result of waves crashing against the shore by the coast. And so this measurement was actually taken in our lab here in Tucson, about 154 miles from the closest coast. But that signal propagates through the ground, and we're able to measure it in our lab here in Tucson, Arizona. So our systems are sensitive enough to pick up these type of signals. And so these can also be used as seismometers at these really low frequencies. So I mentioned the triaxial accelerometer. We're working to expand out. We recently received funding from the NASA Planetary Worlds project to develop this triaxial linear accelerometer into a system that could be sent into space to other worlds, places like the moon or other planets, where it could be used, as I mentioned, as a seismometer for those planets. We are also expanding further on this triaxial design. We also just recently received funding, well, I guess it was about a year ago, to expand this into a 6 degrees of freedom sensing unit. This is our ODIN project called the Optomechanical Distributed Instrument for Inertial Sensing and Navigation, ODIN for short. This is the project that I predominantly work on currently. This is what I'm the payload manager for. So it is an array of these resonator units that are situated in a design that allows us to sense both the 3 linear accelerations as well as the 3 angular accelerations. And shown here, I can't go into too much detail about the project itself, but shown here you can see our requirements and our goals for the sensitivities plotted alongside, again, those GRACE and the GRACE-Followin accelerometers. And then on the right is our additional angular acceleration sensitivity. We see a requirement and goals and for this system that we anticipate reaching once this is launched into space. So this is slotted for launch in 2027. We're currently working on developing it and getting it ready for launch. We're going to be flying alongside the University of Florida's Gratis mission. And this is funded by the NASA INVEST project, which is the in-space validation for Earth science technology. So yeah, this is kind of an overview of the different projects that we're working on that are related to space-based missions. So this is our group. If you have any questions, please feel free to ask. Thank you, everyone. Sorry if I talked a little fast. Yes.
Out of curiosity, and I apologize if I missed it, how much power is required?
Yeah. For the lasers. So we typically, so depending on which laser we're using, the 5 hertz one, we were using a 30 milliwatt laser. And that's split into, I don't know if I don't have the diagram here, but that's split into 2 AOMs currently. So the actual power going into our interferometers is typically closer to about 2 milliwatts. Yeah. Thank you, everyone.